In this video, we're going to talk about an introduction to normal distributions. So when we talk about a normal distribution, we're talking about a set of data that is centered primarily in the middle and is normally distributed, so equal on either side. You've heard of left skewed, right skewed. This is your typical bell curve. So normal distributions have data where it's centered around the mean, which I'm denoting here as mu, the Greek symbol. The mean, median, and mode of a normal distribution are equal. And so when you think about it, if the majority of my data falls within the middle of my normal distribution, the mean and median and mode would also be in the middle, which would be equal. In the normal distribution, or a normal distribution, the area under the normal curve is equal to 1. Normal distributions are denser in the middle and less in the tails, and defined by two parameters, the mean and standard deviation. Now, for standard deviation, I'm going to use the Greek symbol sigma. Now, the reason I'm talking about parameters, and we'll talk more about that later, is a parameter deals with a population. And so this mu and sigma for mean and standard deviation deal with a specific parameter or the parameters of a data set within a given population. So notice when we're drawing out our normal curves, we typically go 3 standard deviations out. So if I start at mu and I add 1 standard deviation, add 2, add 3, and then subtract 1, subtract 2, subtract 3. So what happens when we have 2 different data sets and we want to take a piece from one data set and then another piece or another point from another data set and put them on the same normal curve? Well, that's where z-scores come into play. Z-scores are an indication of how many standard deviations above or below the mean a given data point is located. Z-scores are used to compare 2 or more different data sets from different scales. So the best example that we use is SAT scores versus ACT scores, 2 different grading scales, but yet we can, and by we, colleges can normalize these to compare students' results. The formula that we use for z-scores is as follows: z equals x minus x bar divided by s, where x is the data point, x bar is the mean, and s is the standard deviation. So let's look at some examples of what we would use z-scores for. So the mean SAT score for Math Verbal is 1500 with a standard deviation of 240 points. The mean for ACT score is 21 with a standard deviation of 6 points. Kathy scored a 30 on the ACT. Peter scored a 1380 on the SAT. Who performed better? So once again, 2 different data points from different grading scales. How do we compare the 2? So if we want to look at our normal distribution, when we're talking z-scores, we're going to look at the mean, median, mode being 0. And whatever our z-scores are going to be, it's going to be how many standard deviations above or below. So to find Kathy's z-score, I'm going to take her score, subtract it by the mean of her data set, which is the ACT 21, divided by the standard deviation, and I'm going to get a z-score of 1.5. So her score is 1.5 standard deviations above the mean, whereas our friend Peter, z-score, I'm going to take his score, subtract it from the mean of his data set, which is the SAT, and then divide it by the standard deviation. And when I do that, I get a z-score of negative 0.5, meaning his score is half a deviation below the mean. So that negative z-score value would be below the mean. So looking at the 2, who did better? Well, Kathy performed better on the test because even though her score is lower, based on the scale and based on the standard deviation and means, when I normalize these 2 scores and put them on a normal distribution, I see that Kathy performed higher. Now, let's look at the next example. Kyle z-score was 2.3, what was his ACT score? So this is asking us to work backwards. Given a z-score, let's find his real score. So we don't know the data point. So if it's ACT, we're going to use the same mean, 21, and the standard deviation of 6. And so by multiplying by 6, and then adding 21, I get his score of 34.8. So what happens when these z-scores help us to compare different data sets, but what happens when we want to calculate a probability of an event occurring within a normal distribution or within a specific data set? So we have these different probability distribution functions. So the first is a normal density function. And the normal density function finds the probability of a single event occurring. And so the syntax for this is, for what we're going to put in the calculator, normal PDF, x being the score that we want to calculate the probability at, mu being the mean, and sigma being the standard deviation. The cumulative distribution function, norm CDF, finds the probability of an event occurring within specific bounds. So less than 16, greater than 27, between 16 and 27, all of those are different bounds. The syntax for the calculator instructions are the normal CDF, the lower bound, the upper bound, mu for mean, and then sigma for standard deviation. The last function that we use is the inverse normal probability. This finds a value given the lower probability. So given the bottom 10%, what score would put us in at that level? And so the syntax for our calculator would be inverse norm, lower percent, or the lower probability, and mu, and then standard deviation, sigma. So when I'm talking about lower probabilities, it all comes back to the fact that given a normal distribution, the area under this curve is 1, which when you think about probabilities, 1 translates to 100% probability. And so the entire area under this curve, within this data, the probability of one of these events occurring is 100%. However, to find the probability of a single event occurring, that's where we use that normal density function, the PDF. So that looks for, given, if I were to put this on the x and y axis, given an x value, find the y probability. And y is the point that lies on the curve. The CDF represents the area under the curve from a given value and below or between or above, whichever, using your lower and upper bounds. And so if the area under the whole curve is 1, but we find the area to be 0.15, that translates to 15% probability. And then inverse norm would be, given a y value, find the x in the calculator. All of these are done using calculator functions, but I want you to get an idea of what the calculator is actually doing. So let's look at some examples of this. So the mean length of time Americans keep their car is 5.3 years, with a standard deviation of 1.2. If a person buys a car, find the probability they will own it for less than 2.5 years. So I've already kind of sketched out a normal distribution curve centered around the mean going 3 standard deviations below and above. So less than 2.5 would put us here. And if I want to find the probability less than, all right, that's the area under the curve. So my lower bound here is, if you think of it as a function, our function as it approaches, as x approaches negative infinity, y approaches 0, and so x is approaching a negative infinity. So since I'm trying to find the area under the curve, I'm going to be using that cumulative, so the CDF function. So remember the syntax. The lower bound is first. Well, since we can't actually say a negative infinity, we're going to put negative 1e99, which represents negative 1 times 10 raised to the 99th. And what that does is it gives us a number small enough to get the lower bound or the lower tail of this function. Then we're going to do the upper bound, which is the score 2.5, and then the mean of 5.3 with a standard deviation of 1.2. And so what that looks like is if I take my calculator and I say second vars, which is distributions, go down to normal CDF and press enter. Now, a lot of yours is not going to look like this because this prompts you with what you need to put in. A lot of you are going to have to remember the syntax because the TI-83 calculators make you put it in as a list. So if the lower bound is negative 1E99, the upper bound 2.5 with a mean of 5.3 and a standard deviation of 1.2, a lot of yours will look like this where you have to actually input the list. I get 0.0098, which represents, in probability terms, 0.98%. And so what this tells me is the probability that an American who buys a car will own it for less than 2.5 years is 0.98%. So now let's find exactly 3 years, the probability of them owning a car for exactly 3 years. And so how we would do this is exactly refers to the density function, or that PDF. And so the score here, exactly 3. So when x is 3, we want to find that y value on the curve. So 3 with a median of 5.3, or a mean of 5.3, and a standard deviation of 1.2. Again, to do the PDF, we go to second vars, go to the PDF. For x value, the 3, and then the 5.3, and then the 1.2. And we get 0.05297, which in terms of probability is we'll round to the nearest tenth, 5.3%. So, and if you think about it in context, the area under this curve represented 0.98%, while the area, or this value here, would be 5.3%. And as you see, I'm increasing the area, and you can kind of think of it as the area as it goes just for this value here at 3. It makes sense as the curve increases and decreases again. Now let's look at the probability that an American who buys a car will own it between 3 and 6 years. So between 3 and 6 years, we want to find the area all under the curve here. So the reason I have us sketch it is we want to look at it and say, okay, well, this looks like a lot more than the first probability that we found. So and as it should be, because more of the data lies within the middle of our distribution. Since it's a bound, we're going to use the cumulative distribution. The lower bound here would be 3, the upper 6 with a 5.3 and 1.2, and I would get a value of 69.25%, which absolutely makes sense in context here. So the probability that an American will own a car between 3 and 6 years is almost 70%, 69.25. Now, more than 7 years. All right, well, this is saying 7 years and more, so I'm approaching a positive infinity. So once again, cumulative distribution function. My lower bound in this case, though, was 7, with an upper bound of positive infinity. You guessed it, it's the positive version of what we represented as negative infinity. The same standard, or mean and standard deviation. And when I do this, I get approximately 7.83%, which once again makes context and makes sense in terms of the context here. So the last example we're going to look at is what number of years would John need to own his car to be in the 90th percentile. So 90th percentiles, what percentiles tell us is that 90% of the population is below your score. So you're looking at the top 10%. So that 90th percentile represents the bottom probability. So since it's the bottom probability is given, we're going to use the inverse normal function. And so with the inverse normal function, we put in the bottom percent, which is 0.90 for the probability, and then the 5.3 for mean and 1.2 for standard deviation. And when I do this, I get 6.84. And so that, in context, would mean 6.84 years. So in order for John to be in the 90th percentile, he would have to own his car for 6.84 years, which when you really think about it in context, the 90th percentile is the top 10%. And so if 7 years was 7.83, it makes sense that the top 10% would be slightly less than the 6.84. So just to recap, we've talked about normal distribution as the bell curve, and then using z-scores to take two different data sets and normalize them so that we can compare their data points. Well, then we also went a step further to say, okay, let's find the probabilities of a certain event within a normal distributed data set. Thanks for watching.